Okay, so today we're mostly going to look at some different types of integration that are going to deal with some of those transcendental functions, some of those functions, the trig, the e's, the natural logs, those sort of things that we're going to see. So we've really already done one like this. This is a really basic trig one. We've got the integral from, or not, we just have the integral of sine of 3x dx. So right here, our 3x is going to be our u. So our u for this is 3x. That means our du is just going to be 3 dx. So we need a 3 with our dx right here. And if we put a 3 there, it means we got to put a 1/3 out front to balance that out. So this 3x is our u. This part right here is our du. So when we convert this to u's, when we substitute, it's going to look like this. We'll have the 1/3 sine of u du. And once you get it to the place where you have plugged in your u and du, you should have something that you can integrate fairly easily, something that you can integrate using just trig rules, power rules, something like that. So here, what is our integral of sine of u? Is negative cosine. So we're going to have negative 1/3 cosine of u plus c. And if we substitute back in, it's going to be negative 1/3 cosine of 3x plus c. Questions? Here is our next one that is a little bit more complicated. So, when we look at this one, we have the integral from, just the integral of sine 5x cosine 5x. It feels like 5x should be your inside part, right? Or based on what we've done so far, looking at that last one. So 5x could be your inside part. The problem is if you use 5x, so don't do this because it's not going to work out for us, but if we had this was our u, right, we could put a 5 here, we could put a 1/5 out here, that'd be fine. The problem is that we end up having to try to integrate sine u cosine u. If we do that, do we know how to integrate sine u cosine u? It's two trig functions multiplied together. We do not. We only know how to integrate just basic trig stuff that has rules for it. So we can integrate sine by itself or cosine by itself, but not those two multiplied together. So we can't take the same approach on this one as we did the last problem. Our u is going to have to be something bigger. So what do you guys think? we cannot. If there was a plus sign in between them, we could do that, a plus or minus. But integrals cannot be split for multiplication. So, so that's a good thought, but it will not work. Let's think of it this way. What if I let u be sine of 5x? What is the derivative of sine? It would be cosine of 5x, but that would be a chain rule, right? And I'd have to multiply by 5, so it would be 5 cosine 5x, and then we'll put the dx with it. So let's think about what I've just done. I made this whole thing right here u. Do I have my du that I need there? Almost, right? Because for my du, I need 5 cosine 5x dx. I've got the cosine 5x dx part. The only thing that's missing is a 5. That's just a coefficient, so I can add it in right here as long as I put a 1/5 out here. So this part right here is going to be my du. So I had to pick a whole piece of the function that I could take its derivative and that other part would still be in my expression. So that means when I convert this, it's going to look like this. There are no sines or cosines left because the entire thing, sine of 5x, is going to just be our u. And then this whole thing, 5 cosine 5x dx, that is my du. Oh, and I need the 1/5 out front. Thank you. Okay? So I'm just going to integrate this. I'm going to have u squared to the 1, and I'll have 1 divided by 2 here. I still have my 1/5 that is out here. Make sure you put the plus c on the end. And so if I multiply my 1/5 and my 1/2 together, I get 1/10. And then I'm going to go ahead and plug back in. I've got sine of 5x squared plus c. They are probably going to write it like this. Sine squared of 5x plus c. There, and that would be your answer. Question for you. Did I have to do it that way? Could I have done it a different way? I could. So if I wanted to, now I think it's a little bit easier to do it this way because you don't have any negatives that you have to deal with. But I could have used cosine of 5x. Excuse me. I could have used cosine of 5x as my u, because the derivative of cosine 5x would have been negative 5 sine 5x. I could have put the negative 5 here, the negative 1/5 out front. My answer would have a cosine in it if I did it that way, but they would be equivalent expressions that you could use like trig identities to make them match. Although there would be some trig identities I think that we don't know. So, but we could have done it the other way. Yeah, sometimes it is going to matter which one you pick, and sometimes it does not, depending on what you're dealing with. In terms of sine and like if it's sine and cosine, it usually does not matter which one you pick if they're just multiplied together like that because they are the derivatives of each other, so you can pick either one. We're going to see, I think, maybe the next problem where it will matter which one you pick. So, actually, yeah, it does matter on this one. Okay, so we need to decide here, this is similar to the last problem, we need to decide what we're going to use for our u. Like the last problem, 3x is not going to work. If it was just a tangent or a tangent secant or something we could actually integrate, then we could use the 3x. But no, using substitution is how you have to deal with it. So we have our chain rule and our quotient rule and our product rule for taking derivatives. Basically, we have to use substitution to go backwards from any of those. And some of those things, substitution will not work for, depending on what type. Really, chain rule is mostly the main one that we look at. So there are some other methods that can be used that we don't have to go into because substitution is the only one that we look at. There's also some like trig differentiation, logarithmic differentiation, like some different stuff that you'll probably learn in Calc 2 in college if you take it. But we're not necessarily going to, at the end of this class, be able to reverse everything we did with derivatives. So there are no, like, rules. Substitution is the way that you deal with it. And for, I want to say for, like, quotient rule, you got to use, like, a different type of substitution for that. We will see some that we can do because we're going to, the notes that we're going to do tomorrow will have some that would have been like a quotient rule and we'll be able to deal with those. But there's not like a product rule or anything for those that I am aware of. I have not seen any of that ever done that way. So what we want to do here is we need to pick something where when I take the derivative, I get another part that is there, right? So 3x would be too small. Probably either tangent or secant is what we would want to use. What is the derivative of tangent? Secant squared. Okay. What's the derivative of secant? Secant is 1 over cosine, but its derivative is secant tangent. So tangent is going to be better to use here because if I let u be tangent of 3x, then du is secant squared of 3x, and you got to use a chain rule there, so you'll have a 3 right here. We'll put our dx over here on the end. Whereas if I use secant, my derivative is going to be secant tangent, and I don't have an extra secant right here that I can use to have secant tangent, plus that tangent is cubed, so it's going to be an issue. So sometimes you just kind of have to try it both ways and see which one gives you the correct derivative. So what I have done here, actually I'm going to write it this way. It's also important to remember that when I see tangent cubed 3x, what it means is I've got tangent of 3x cubed, and then secant squared 3x dx. So this part right here, this tangent 3x is my u. And then I don't quite have the du that I need. What is missing from my du? The 3. So, but that's okay. As long as it's just a coefficient, I can just multiply by that 3 here and put a 1/3 out front. So then this part right here is my du. So this is going to give me 1/3 integral of u cubed du. Okay, so for this, we're just going to use our rules. So we're going to have u to the 4th power. Got the 1/3 out front. We're going to do 1/4 right here, plus c on the end. So we will end up with 1/12 When we're plugging back in, it's going to look like this: tangent of 3x to the fourth power plus c. But you will probably see them write it like this: 1/12 tangent to the fourth plus c. These two expressions mean the same thing. Just you're probably going to see if it's multiple choice that notation used right there. I'm just showing every one of those steps to be very clear about what is happening, but you don't necessarily have to show all those. I should put my string of equal signs here. Okay. Questions? Let's see. That is a square on top and then a fourth power on the bottom. Okay. So for example, alright, we've got secant squared x on top, tangent to the fourth x on the bottom. What do you guys think we should use for our u? Tangent. Because generally a lot of times if you're seeing a tangent and there is a secant squared somewhere, tangent's going to be your better option. So u is going to be tangent x, du is going to be secant squared x dx. So we're going to have to do a little bit of manipulation on this, but we have our u and du here. So I'm going to rewrite it this way. Whenever I have a fraction, I could split it apart and do 1 over tangent. I'm going to write it this way: tangent x to the fourth power, because that's what that means, and that helps me visualize my u a little bit more. And then the secant squared x would be here, and then we'd have the dx there. So that secant squared x, because it's in the numerator, is over 1. That dx is also numerator. It's going to be there with it. So, you can do this just in your head, or you can actually write it out like I've done here. So this tangent x is our u, and then we already have our whole du right here. So we are not going to have to add any coefficients or anything in this time. So we will have 1 over u to the fourth du, which is better to think of as u to the negative fourth. Du for your rules. And so when we use the power rule to integrate this, we would have u to the negative third, and we would have to divide that 1 out front by that negative 3, which will give us a negative 1/3 here, and put the plus c on the end. So you will probably see that u come back down to the bottom, and then you got to plug that tangent back in. So negative 1 over 3 tangent cubed x plus c. Okay. Questions there? Did I not do? Yeah, it's in there. We're gonna skip something else first though. Okay, so this is very similar to a lot of the problems we did the other day. It's not got the trig. On the surface, it doesn't look like there's anything weird about this problem. You just have a denominator here, so we would use that as our u. So we'll have 3x minus 2. Our du is just going to be 3 dx. We need a 3 there with our dx, so we would just multiply on the inside by that 3 and the outside by that 1/3. So this part right here is our u. This part right here is our du. And so we are going to end up with 1/3 integral of 1 over u du. And what is the integral of 1 over u? Natural log. So that this one like doesn't immediately appear like it's going to have anything strange about it. But if you're thinking of it like u to the -1, remember if we're trying to integrate that u to the -1, if you try to use power rule, you get u to the 0, and then you find yourself doing 1 over 0 out front, which can't happen because it's undefined. So that should remind you here that this is natural log. So we got 1/3 natural log of the absolute value of 3x minus 2 plus c. I skipped a step there. You get 1/3 natural log of u, absolute value of u, plus c. I've skipped straight to plugging in the x. It's fine if you do that. There. Okay, questions? Let's try another. All right, so we've got integral of x squared over x to the 3rd minus 8 dx. Could I use love connection on this one? I could not because it would be upside down. Right? Like if I tried to divide it, it would look like this, and our heart is upside down, and that would be no good. We cannot do love connection upside down. So this is not a love connection problem, but if it were flipped, it would be one that you could do a love connection problem with, and you wouldn't actually have to use substitution for it all. So what do you guys think I should use for the u? X cubed? What about the minus 8? Should I go with it or no? I could kind of do it either way, but it's going to be easier. Like that when I take the derivative of the 8, it just goes away. right? So you want to include as much as you can, as long as it's not going to give you something in your derivative that you don't have there. So the u, I'm going to do x cubed minus 8. And you'll find in a lot of these problems that we do, the denominator is a very good thing to use for your u a lot of times. Not always, but a lot of times. And so the derivative of that would be 3x squared dx. So again, we can think of this as 1 over x cubed minus 8 times this x squared dx here, because that numerator, you know, you can put stuff over 1. So you can think of like pulling that apart. So I almost have my du. I've got the x squared. I'm missing the 3. So like we've done on so many of these, we're going to add that coefficient in there, which means we've got to divide out front by that same number, so we get 1/3 out front. And so we've got a u right here. We've got our du right here. So it's going to look like this, 1/3 integral of 1 over u du. What is the integral of 1 over u? Natural log. So we got 1/3 natural log absolute value of u plus c. If we plug in our u, we got 1/3 natural log absolute value of x cubed minus 8 plus c. Okay, questions there? Be careful with this, because what I usually see is students start to do problems, and anytime there's a denominator, they start throwing natural log in there. If this was to the 3rd power in the bottom, it'd be 1 over u cubed, which would be u to -3, which we just use power rule stuff for, right? So just because there's a denominator doesn't mean there's a natural log. But we're going to see a lot of problems like this, and sometimes students just start putting natural logs every time. There. Okay. This time we've got natural log of x to the 3rd over x. And I just told you the denominator is a good thing to use for your u. Or a lot of times. Would it be good here? It really wouldn't do anything here except for change your x's to u's in that case, right? Your x would be your x would become a u, your dx would become a du, but you'd still be looking at the same problem if you did that. So it's not going to be helpful to do that this time. What could we use for our u? Natural log of x. So if I let u be natural log of x, what is du? 1 over x dx. So like we've done on these other problems, we can kind of split that fraction apart. This is the natural log of x to the 3rd power. That's my numerator. It's over 1. And I can pull apart over here. This is 1 over x. And we got that dx with it. So natural log of x is our u. Our 1 over x dx is our du. We have everything we need. We do not need to split this up. So we are going to be integrating u to the 3rd power du. So that would be u to the 4th. We've got to divide out front by that 4. Put a plus c on the end. So we would get 1/4 natural log of x to the 4th power plus c. When you integrate, when you use that power rule, when you're going to drop that integration sign. And what you should see happening too, when you drop the integration sign, when you're using this power rule, the du, mathematically this is not what's happening, but the du becomes the plus c. All right, so when that integral sign goes away, the plus c should appear, unless you're doing that definite integral where you would plug numbers in, but most of these are just going to be general for right now. Okay, questions? All right, I really want to do 8, but I'm going to skip over here to 9 real quick because we need to make sure we get to some of the e's. Good thing is e is going to be pretty basic because the derivative of e is e, so that will work out nicely for us here. So we've got e to the 3x dx. All right, e to the 3x dx here. So what could we use for our u? 3x. So u is going to be 3x, which means du is just 3 dx. And it's good whenever we can get something where our derivative is just a number so that we can very easily add that 3 right there, as long as we also put the 1/3 out front. And so our 3x, that's our u right there. The 3 dx, that's our du. So this will look like this: 1/3 integral e to the u du. What do we get when we integrate e to the u? E to the u, right? So we get 1/3 e to the u plus c here, and then we are just going to plug in the 3x. Yes? I think you will be okay on a very simple one like this if you're doing this stuff in your head. Because I know that I had several students last year that just, if it was an e to the x that just had that extra number there, they were just doing this thought process in their head. I'm pretty sure that is fine, and you don't have to show every step to it. I usually do it this way just so everybody knows, like, it's the same process as it is. It's not a new rule necessarily. It's the same process as it is for all of them. There will be some ways they can ask a question where you would have to kind of show work, but most of the time it would be okay. All right, let me look at what I've got here to see. Let's see, okay. Which one is most important for me to do? Probably this one, and if we have time, I'll do the other. All right, so we're skipping down to 11. I want to use the love connection on this, but I cannot because I'd have to use it upside down. Okay, so what should we use for our u here? I want to say 3x, but that doesn't change a lot about this. I'd still end up with an e to the u and then a 1 plus e to the u on the bottom. It'd still be a complicated expression, right? So I could use just the e to the 3x, and that would help some. But then I still have this 1 plus over here. The 1 doesn't give us an issue, though, right? Because if we use 1 plus e to the 3x as our u, then when I take the derivative of that, the derivative of 1 is 0, so it's going to go away. So that's probably our best bet. The derivative of e to the 3x is e to the 3x, but you must use a chain rule for that. So you got to have a 3 right there, and then dx. So again, I'm going to kind of split this up like I've done with all the other fractions. I'm going to write it this way. 1 over 1 plus e to the 3x times e to the 3x dx. So right here, I've got my u right here. I've almost got my du, but I am missing a 3 with it here, which means I need to put a 1/3 out front. So that will give me du right here. And so I'm going to get 1/3 integral of 1 over u du. What is the integral of 1 over u? Natural log. So natural log, absolute value of u plus c. So my answer would be 1/3 natural log, absolute value of 1 plus e to the 3x plus c. Sometimes you will see them drop the absolute value bars on one like this. Why and can you do that? E is always positive. You've got 1 plus a positive number. So since that is always positive, the absolute value bars are fine to leave there. In fact, I would just leave them there if it's free response because they don't hurt anything being there. But they're not necessary because that's always a positive value. So sometimes you'll see them drop those if that is always a positive value right there. Okay, questions? All right, get off of whatever you're on there, Connor. You're distracting the whole back row. All right. One more thing, real quick. All right. What am I actually integrating here? This is tangent, right? Because this is just the same as tangent of theta. But do I have any rules for integrating tangent? I can take the derivative of tangent, but I don't know how to integrate tangent. So they are not going to ask you just to integrate tangent of theta. They're going to give it to you like this, sine of theta over cosine theta, I think, is best I can tell. There's a chance you see tangent. If you do see tangent, they're wanting you to use u substitution for this. There is not like a special rule for that. So let's let this denominator be our u. What is the derivative of cosine? It is negative sine of theta. And we'll put a d theta with it since theta is a variable. We're going to have that instead. So if I kind of split this up like I've done the other fractions, I've got 1 over cosine theta times sine theta d theta. I need a negative with that sign. I can do that as long as I also put a negative out front, because we'll cancel each other out. So this denominator right here is my u. This stuff over here is my du. And so I would have negative integral of 1 over u du. What is our integral of 1 over u? Natural log of the absolute value of u plus c. So I end up with negative natural log absolute value of cosine theta plus c. To me, it's kind of crazy how natural log finds its way into the derivative of a trig function. All right, I think what I had there on the end is not right. Let's look at Canvas to see what you guys have. Oh, yes, I do have those. I'll give those to you. So your assignment comes from a couple pages. So it's page 341, 31 through 45 odd, and then 351, 1 through 9 odd, and 13.